Hello, and welcome to the final video presentation for Team 4 for ECE 4534 Embedded System Design. So in this, I'm first going to give a little introduction to our project. The goal of this project is to create an autonomous robot bartender. This means that we have a rover which will navigate from a starting position to a place where we put a robotic arm. The rover will then navigate to this robotic arm. The user who is using this system will then pick a drink with a graphical user interface for the arm to create. The arm will then mix this drink into a cup that is sitting on the rover, and then the rover will then return from the arm to its original location with the drink in tow. And for this project, there are four different components to it. The three-wheeled rover, which is being worked on by Quentin, a robotic arm, which is being worked on by Jonathan, sensors to run the three-wheeled rover, worked on by Morgan, and then finally a navigation algorithm to guide the rover to the robotic arm, which is being worked on by Luke.
Hello, my name is Morgan Welch, and I worked on the sensor systems for our autonomous delivery system. The system involves ultrasonic sensors for distance, so that we can sense where our objects or walls are. It also involves a load sensor that measures the mass in a cup on our rover. Even though I was unable to finish the implementation of the load sensor, I'm going to still talk about it in this video. I will begin with the constraints of the sensors. The ultrasonic sensor, one of them reads distances from 3 centimeters to 400 centimeters, but the other three can read from 3 centimeters to 200 centimeters. The sensors had to be strategically placed, so I thought the best option would be to put the sensor that can read the furthest distance in the front of the rover, so that when the rover is facing something, it's going to read that quicker than it's going to read anything on the side, since it's 200 centimeters on the sides. Another reason they had to be strategically placed was because the sensors cannot cross paths when echoing their sound waves. I solved this constraint by placing a sensor at each cardinal directions on the rover and read them in a round-robin style, so no two sensors would echo at the same time, crossing those paths and interfering with the other's waves. A constraint of the load sensor is the fact that it senses mass from 100 grams to 1500 grams. So either the cup has to be 100 grams, or we must put a plate on the sensor to get above 100 grams, right at 100 grams, when before weighing the contents in the cup. The HX711 module, which is what the load sensor is connected to so the board can read the data from the load sensor, is a 24-bit ADC. This can be strenuous to make sure the right bits are read at the right time and all 24 bits are valid. Next, I'm going to talk about the robustness of the sensor systems. For the ultrasonic sensor, if an object is too small or angled in the wrong way, the sensor won't be able to have an accurate reading to where that object is. The sensor angle is 15 degrees back to the ultrasonic sensor itself, so if that degree is messed up in any way, it's not going to be able to have an accurate reading. Each sensor acquires data every 800 milliseconds. That is fairly quickly, but does leave room for optimization if these sensors needed to be read quicker. If the board is power cycled or reset during the process, all that happens is the board returns to the normal process and begins with sensor 0 and then works its way around in the round robin style, but does not corrupt any data in any way. The robustness of the load sensor is the 24 bits of data are retrieved, but the sensor was not implemented fully by me due to a lack of time. The last thing I'm going to talk about with the sensor systems is the reliability of the two sensors, or rather the two sensor groups. For the ultrasonic sensors, here to the left, you can see this figure of 4 plots, each plotting sensor data. Sensor 0 is the sensor that is facing the front in the north direction. This is the sensor that can read up to 400 centimeters. And each one of these sensors is getting published to a single ultrasonic sensor's topic, and to which I am subscribing to this topic on a Python MQTT client, and using matplotlib, I am plotting this data that you can see here. As far as reliability though, only 2 spikes out of 250 data points are down to 0 on sensor 1. So that shows there's only 2 invalid data points out of 250 data points. It's 2 out of 250, which leads to a error rate of less than 1% when subscribing to this ultrasonic sensors topic. For the reliability of the load sensor, on the right here I'm showing a picture of me getting those 24 bits of data, but I was not able to implement any further due to time. However, I was able to get these 24 bits, but not able to convert them into 2's complement and then get a mass to which would lead to me publishing on a topic that the ARM can read from, so the ARM knows how much it is pouring into a cup. The next thing I'm going to show you in this video is 2 clips. The first clip is the ultrasonic sensors and how they were demonstrated, and the second video, or the second clip, will be of the load sensor and how far that I've got into the implementation of that. This is the ultrasonic sensor system with 4 ultrasonics facing north, south, east, and west on each side of the rover. If you look closely, you can see the sensor numbers. Sensor 0 faces the wall at 200 centimeters. Sensor 1 faces this box at 50 centimeters. Sensor number 2 faces this wall at 100 centimeters, and sensor 3 faces this box at 25 centimeters. And now, if we go over here, you can see that I've plotted the distances to each sensor using an MQTT client. Publishing the ultrasonic data to one topic and then reading each sensor's data to plot this using matplotlib. So it does look noisy. I could not figure out how to change the axes how I wanted to, but if you look, sensor 0 is supposed to be reading 200 centimeters, and it's bouncing between 197 and 198 centimeters, sometimes reaching 199 centimeters. There was just a spike in the sensor 2 data. The sensor 2 is supposed to be at 100 centimeters, and it is bouncing from 97 to 101. Sensor 1 data is supposed to be at 50 centimeters, and it is at 48 centimeters. Sensor 3 data is supposed to be at 25 centimeters, and this goes from 25 to 26. This is the load sensor system using a TAL 221 load sensor that can weigh anywhere from 100 grams to 1500 grams accurately. And it is connected to a 24-bit ADC, the HX711, and then that is connected to the TI board. And it was supposed to work for the cup to sit right here, and when the cup is filled up, strain will be put on the TAL 221 load sensor, and that reading can be sent to the ARM to adjust how much should be poured into the cup. I'm getting 24 bits of data, but I was unable to convert this data from 2's complement form and to move on with this after multiple struggles with the load sensor / force sensors that I tried to use.
Okay, this is Quentin again. Let's talk a little bit more about the 3-wheeled rover, or Rover as I'm going to refer to it. So the Rover, some constraints about the Rover portion of this were the Rover was already built for us and couldn't be changed at all. This means that we couldn't change out any of the motors, we couldn't change out any of to be higher speed or higher torque, even if we wanted to. The Rover had to run the PID algorithm, which we're going to get to in a second. The Rover had to move at least 25 feet, which we were able to test by running it down a hallway. But the one issue with this is because of the novel coronavirus, we weren't able to get together and do a full integration test with 25 feet. And this also runs into, we have to be able to transport our drinks 25 feet as well. We weren't able to test this because we weren't able to do a full project integration. So the PID algorithm is an algorithm that is used to add almost an artificial intelligence to processes and gives them the ability to adjust during execution. This is almost the same idea as if a person were to push on a really, really heavy box and try and move it at a constant rate. If you first start moving it and you start moving the box a lot faster than you want to move it, you're going to decrease the amount that you're pushing on the box. Same thing goes to if you aren't pushing hard enough at the beginning, you're going to start pushing harder. Now this is the same thing that we can do to make motors on the rover move at a set point speed that we want to maintain over the whole of the rover moving. And we use this with the PID algorithm. We can increase the speed of a motor if it seems like it's lagging behind the set point that we want it to, or we can decrease it if it's running way too fast compared to the set point. Now let's talk about some reliability of the rover. So we are having some issues with intermittent crashing during encoder initialization and the SPI transfers. So encoders are things on the motor on the rover which tells us where the rover is, or where the motor is at any given time. The TI board gets a position using a SPI transfer, which you've probably heard about in microcontrollers before, and gets data about where the motor is just as it spins. And from this you can deduce the speed. However, when we're doing our when we're trying to initialize the rover and doing SPI transfers, we get these intermittent crashes. I believe that this is due to encoder data being overwritten or written at wrong times based off of these SPI transfers. However, after getting the rover to initialize, the rover runs very reliably. There might be some crashes every once in a while. However, if you go over and you reset the TI board, you will immediately be able to get the rover running again. Now, the robustness of the system, the one thing about the rover is it's commanded through the navigation algorithm and the using an MQTT protocol, which is a way for each of our TI boards throughout this whole system to communicate with each other. These commands need to have the correct number of data fields, and the data that we're sending is in a JSON format, which is a key value pair of sending data over the air. And these JSON payloads, there are a specific number of data fields that we're looking for. However, if the commands have an incorrect number of data fields, the rover crashes and we have to reset the motor. However, we didn't get a chance to test this rover with the navigation algorithm, so it was a little difficult to sometimes see what would happen, or if the navigation algorithm would give us the incorrect number of fields for these JSON payloads. However, I did some testing and found that if there was an incorrect number, the rover would crash. But as I said before in the reliability, if you went over and reset the rover, it would come back online pretty quickly. And then after this, it could then keep executing the navigation algorithm's commands as well. But we didn't get a chance to, along with this robustness, we were trying to see if we could get around obstacles with the rover, and we weren't able to test this because the navigation algorithm, we couldn't do the full integration and test the obstacle avoidance. So here we can see the rover. It is currently running and publishing to the MQTT right here. This is actually, I'm about to send it a command. Right now I'm going to send it a command over the MQTT to move forward. So I press it, send it a command, rover starts to move forward. I then send it in a direction, I tell it to stop. The rover stops. I then tell the rover to come back towards me. And these are all commands that will be coming from the navigation system as well. And I can also turn it. Let's turn it to the left. It's small movements, but it turns to the left. And then let's turn it as well to the right, where we can see the rover turning to the right.
The navigation algorithm makes a few assumptions about the environment the rover will be in. First, it assumes that the arena that the rover operates in is walled in on all four sides. Second, it assumes that the drink station, which the rover is attempting to find, is along one of the walls. It also makes assumptions about the maximum size and potential positions of obstacles. Because we weren't able to integrate, I created a simulation program using the Python game graphics library, Pygame, to test the navigation algorithm. Instead of ultrasonic sensors, synthetic sensor data is created using ray tracing from line segments placed around the rover. The Python program uses PAHO MQTT to connect to the Raspberry Pi server and publishes and subscribes to the navigation topics. The board publishes and subscribes to those same topics to set up communication with the Python simulation. Every so often, the Python program sends sensor data to the board, and based on the sensor values, it determines whether to stay in its current navigation state or to move to another navigation state. The algorithm is robust to different configurations of obstacles, different drink station positions, and incomplete sensor data. Because I was not able to test the algorithm with the actual rover, it is hard to say how well the algorithm would perform when it would have to deal with all of the real-world factors it could encounter. I believe it would still perform reasonably well, and with some additional testing and tweaking, the algorithm could reliably get the rover from point A to point B. Here is an example of the navigation algorithm working with the Python program. The green square is the rover, the red rectangles are obstacles, and the gray square at the bottom is the drink station. The raycasts that determine the sensor data can be seen around the rover, and their current values are listed in the bottom right. The simulation is able to show that the navigation algorithm can find a wall, travel along it while avoiding obstacles, and reach its destination at the bottom. Here, we can see that the rover determines it can move back to the wall after avoiding the first obstacle, but it quickly realizes that it must again avoid another obstacle, so it moves back out.
The ARM consists of 6 digital servos, which are controlled by the PCA9865 EWM generator. The communication to this chip is done via I2C. All the servos, with the exception of the base servo, have a rotation angle of about 180 degrees, while the base one is capable of doing about 300 degrees. The ARM receives drink requests via Wi-Fi using the MQTT protocol. JSON format is used for each message transmitted, so that way it can easily be parsed by the receiver. And the only part that the user must interact with is the Python script, which creates a simple GUI that the user can select which quantities of each drink that they would like. Once the ARM will receive a request, it then waits for the rover to be docked. Once it is signaled that the rover has been docked, it will then begin a sequence of serving each drink. The ARM is then able to pick up and pour the specified quantity of each drink, and then put that drink back into its original location. Once the drink request has been fulfilled, the ARM will then signal back to the server that the request has been fulfilled, and the rover will be undocked. The ARM is able to handle any number of drink requests, but if the drink requests exceed the queue size stored in the drink requests, the rest of the messages will be thrown out and an error message will be sent to the graphics user interface. And although this demonstration was coded to handle 4 drinks with very few changes of code in it, you can easily scale it to any size. And the arm can also reconnect itself to the Wi-Fi access point, even if the connection is interrupted. Unfortunately, the arm didn't implement the ability to search for drinks, which would have been accomplished using the ultrasonic distance sensor. This wasn't implemented due to the COVID-19 shutdown of the VT labs, preventing the ability to print a custom mount for the ultrasonic.